At the end of the day, getting at the scale is really about getting access to that capital. I'm not worried at all. Or about quantum computing. Let's put it like that. So I mean, I believe that what we're going to do, and I think AI is going to be critical to this, is we're going to hand a set of tools to people that are just unused to having a computational tool like we're talking about. There's another manufacturing revolution. And it's just that manufacturing revolution or industrial revolution happens on a wildly different scale. There's no wall we've hit by any stretch of the imagination. Over a year ago, we had announced at Quantum World Congress, we're still on a path where we're going to 10x the system size every time. The rate of change of what can be computed, of what computation allows one to do, is just so fundamentally different now and in the future, that governments are going to have to figure out what it means to control these resources.
Welcome to another episode of the Quantum Economy Podcast. My guest today is Ben Bloom, CEO of Atom Computing, a driving force behind the new era of quantum machines. Ben started his journey as a physicist, helping build one of the most accurate atomic clocks ever made. Now he's again pushing the limits, leading a company that is using neutral atoms to build a scalable quantum computer. Ben and I talk about the patience that is required to build in quantum and what it means to lead at the edge of science and industry. This is an episode into the future of quantum computing and the new era of scientific and industrial progress that it's opening. Welcome to the Quantum Economy Podcast with Ben Bloom.
Yeah, so Ben, thank you for coming on. I just came off a conversation where someone started to talk to me about Chicago being the quantum center of the world. A lot of things happening there as well. But I had the privilege to visit Boulder, Colorado, having taken the Dumb and Dumber route through Nebraska earlier this year. So you're in Boulder right now, aren't you? And it's a very exciting time, and it's very also interesting. And just to start it off, where is the quantum capital of the world, Ben?
Ooh, now I have to be a little careful. So let me put it like this. I think Chicago is a great place. I think that when you look at where there are a lot of quantum companies, where there's a lot of actual practitioners of quantum computing, Boulder, the Denver area is leading. The U.S. government denoted it a technology hub in this Boulder, Denver area, and that was codified with this creation of Elevate Quantum. But even when you think about just pure numbers of people and companies, Atoms here, Quantinuum's here, Inflection's here, Oxford Ionics is here, and that's just the quantum computing companies. There's also places that are in the supply chain doing lasers, like Vescent. There's places in the supply chain doing dilution refrigerators, like Maybell. I think that just purely based off of companies and number of people working on quantum, it's hard to compete.
So now we set that straight once and for all. No, I mean, it's just interesting at all the things that are happening, and it's I'm trying to keep up and follow these companies and all the initiatives around the world. It's been a very exciting year, and just to start off, with your neutral atoms approach, and we can talk a little bit about your company and what you've done in that sense. But I just want to be curious, how would you look at, I would say, this elegant approach that was obviously also from a scientific standpoint, always as a promising one, but challenging to scale and all the things that we have. How would you look at neutral atoms? How has it changed in compared to other competitors over just the past, I would say, 12 to 18 months?
Well, 12 to 18 months, I think it's really entered into the zeitgeist and entered into, I would argue, the lead. But I mean, you could argue it's now competing for the lead across quantum computing. I think if you look at what Jensen Huang said on stage about neutral atoms just yesterday at GTC, I was amazed and excited about how it was just a given that neutral atoms are one of the three major players in quantum computing. If you look at the All In podcast with John Martinez just the other day, Even though he's done amazing work with superconducting qubits, spent most of his entire life and career working on that. He said, look, there's a newcomer and there's a lot to be done there. And it's pretty exciting. Um, I think that the reason why the last 12 to 18 months have been so amazing for neutral atoms isn't because they are the best at anything. Even though I started the company, to build neutral atom quantum computers, I started it with my eyes wide open, knowing that they have big negatives and big positives around neutral atoms. But the critical thing is that they have enough positives that it's easy to holistically get everything working. And that's actually, in the end, what most matters to a quantum computer. It's not whether you're, specifically good at one operation. It's going to be, how does the actual computer work? How does running an algorithm, how does running logical qubit circuits work on it? And that's where I think neutral atoms have really started taking the lead.
What do you see like right now as like the unsolved engineering risks for like the next level of scaling to neutral atoms?
Oh, I think it's the same pretty much across the entire board, which is it's all about classical control and how you scale that classical control. So we have systems with 1,000 qubits. We sold one to Novo Nordisk Foundation. We have systems with hundreds of qubits right now. We have, but I mean, we're also starting to build systems with 10,000 qubits. But generally speaking, every time we go up in scale, it's the problem for us is just a classical control problem, which is we need to create spots of light, a whole lot of spots of light, and control those spots of light so that we can rotate the atom's quantum state, we can entangle atoms, and so on and so forth. And so you're really building, conventional optoelectronics, but you're building it at a size and scale, or I should say, a size and speed that's unlike anything else in the market. Now, I say that because we are talking to each other on screens with literally millions of pixels that are creating little spots of light, and it works quite well. But I'll admit, it works quite well at 120 hertz or 240 hertz. And we don't want our quantum computer to run at hundreds of hertz. We want it to run significantly faster than that. You can do neutral atom gates on the order of 100 nanoseconds. So that is the kind of scale we need to get to for these optoelectronic devices.
And I think theoretically that's a straight path. And what we see is that we put more money into it, more people, more brains into it. We overcome these hurdles and we make progress. But if you look at it from an organizational standpoint, if you look at giants like Google and IBM and their capacities to fabricate, is there a challenge here also on that level for atoms and your approach in that sense? Because I mean, these companies are basically, they have unlimited access to resources and capital.
Yeah, I mean, there's no question that, as we get to larger and larger systems, it's access to capital is going to be critical. I think that, whenever you talk about building a new technology, at the end of the day, getting it to scale is really about getting access to that capital. I would say the thing is, when you think about what's difficult to scale superconducting qubits, it's really about how, I would argue, you don't have a good closed loop in your system. I worked on superconducting qubits quite a while ago. And one of the things I noticed was you have an idea, you work with people who are going to fabricate it, they fabricate it, you eventually get it into a refrigerator. And even when you talk about, really fast clips, it's a few months to see, oh, okay, did this work or did this not work? And that's a really, really challenging kind of circle to close. And part of that is that because most of the testing you actually need to do for a lot of these systems is all around the quantum systems themselves, especially for superconducting qubits and things like that. Whereas for atoms, I mean, at the end of the day, the atoms are the atoms. Like you're not going to change anything about them. And so when you're trying to scale, what you're trying to do is scale all this classical control system. And there, you don't need to put it into a dilution refrigerator. You don't need to put it into a cryogenic anything. You need to have it run and put that on a camera. Like that is what we're trying to do, to create spots of light. And a camera can measure spots of light just as well or even better than the atoms most of the time. And so I think that we get a lot of boost from not having to kind of build this with our qubits in the circle, you could say.
But is the optical control a limitation then at the end of the day, or an advantage?
Um, I think it's an advantage. So I think there's a few different ways you could say it's an advantage. One is that you have wires. I always say, okay, our qubits are wireless. That's kind of true. Our qubits are sitting there. They're at the bottom of a microscope objective. So when you want to send signals to the atoms, you're just creating images in the back of that microscope objective and literally relaying it to the atoms. But there are wires. All the optoelectronic devices that create all those spots of light, they have wires in them. Um, but I think that's a much more classically tractable problem than the general wiring challenges that folks at Google or IBM or other superconducting qubit companies are focused on. I mean, I think if you look at the amazing work that's coming out of these companies and you see the pictures that they have behind them of showing off their system, they're still just brute forcing it. I mean, the reason why you talk about, 50 superconducting qubits in 2018, 2019, and 100 now is because brute forcing wires is really, really complicated and hard. And they end up just creating these giant, elegant monstrosities, let's call them.
No, I agree with that. But also here, though, I mean, history is taught us lessons about fruit cases and weird approaches that was discarded, and we look at the whole brute forcing and optimizing and trying to stabilize and what do you see any exotic approaches coming in with error protected qubits or different ways to do the technologies? Are you looking at like a resource project where you see, because I mean, you look at the big giants, you look at superconducting computing, and you could look at, this seems like a path that is progressing. But what if someone comes around the corner with a much more elegant approach? Are there exotic things that you follow that you think are promising?
Well, I think there are things that are promising that I think are elegant on the physics side, but probably much more mundane than people think. I do think erasure conversion, just being able to spot and point out where errors are, which is something that we're pursuing, something that Amazon is pursuing, and probably QCI and other companies like that. And I'm sure to some extent, there's Google and IBM. I'm sure they're paying attention and probably have internal projects on this. So I think there's a lot to be done there. But when we think about, what is the future hold, the qubits we have are pretty good. They're getting better. And I just don't really know if I believe that there's ever going to be a perfect qubit. Like at the end of the day, their qubits we have are pretty amazing. Like I think that we'll get to better and better gate fidelities as neutral atoms. Trapped ions are already at 4 nines of fidelity. At the end of the day, that's a pretty amazing number. And I think probably most people will get there. And it's still going to be that you have to build a classical control system around this. So I think there's a lot of momentum around the qubits we have. And I have a lot of doubt that something magical is going to happen.
Yeah, I mean, you're betting on the elegance of nature, so to speak, right?
Yeah.
But nature can be messy. And what if there is a synthetic qubit approach that is much more scalable than relying on nature? How would that look like?
I mean, I think that a lot of the time when people think that, I feel like they jump to what is the perfect world and they forget all the messiness between where we are now and where they have to be in the end. I actually, before I was working on quantum computing, I was actually building transistors at Intel. And the amount of money and the amount of effort that went into going and building digital switches wildly dwarfs anything that we could possibly imagine doing, I would argue, for quantum computing. And at the end of the day, when things work in that process, you have digital switches, and that's it. You don't have analog computers. You don't have, really, really complicated structures. You just have, you just have CMOS switches. And so I think there's this jump where people think, look, we can mass produce, billions, trillions of transistors. Surely we can mass produce anything, but I actually don't know if I believe that. I feel like most people who say that probably have actually never worked in a fab producing millions or billions or trillions of transistors. Um, so I don't know. I think I'll be pleasantly surprised one day if a magic qubit comes. Um, but I'm not going to hold my breath for it.
So we cover a little bit about the background of the technology all the way to magic qubits. I'm also curious about your journey as a founder, as an entrepreneur. You've jumped between the roles of being a CEO and a CTO back and forth. I mean, obviously you're a tech person, but you also have a passion for building a company. Um, Tell me a little bit about the journey of setting up the company, the lessons learned as a founder and as a leader, but also yet like your passion towards being the CEO of the company, still being so heavily involved, obviously, in the sciences and the technology of the company.
Yeah, I mean, I think, it starts pretty much like everyone's journey as a founder, which is, I started off the company alone, and it was just me, writing little PowerPoint decks or whatever, at a coffee shop. And I found a co-founder after a few months. I went and raised money. We started hiring and so on and so forth. I mean, I think that in a really deep tech startup, um, so much is based off of luck and timing, I would argue. Like I said, at the beginning, happy and amazed that neutral atoms are now just considered to be one of the three leading technologies. I mean, I think if you talk to people in 2018 when I started talking about building this company, um, first off, no one outside of academia had ever heard of neutral atoms. But generally speaking, even if they had, they would say, well, what about this? And what about this? And there would be a lot of whataboutisms that I think were based off of, earlier pitches they had heard from other companies and things like that. Maybe not even in neutral atoms, but kind of just generally throwing shade around. And I think that the timing was everything. It was about finding the right partners who could put money into the company, who could support the company, including even the US government with like SBIRs and things like that. And then just constantly building and kind of having to really run. Because I think that was actually one of the things that we learned quickly was that, it wasn't good enough to just match the pace of development of superconducting qubits. We really had to do something that was wildly performant and also wildly fast compared to, all the work that had gone into superconducting qubits. And I think we've delivered on that. Now, I think that, as the company has grown, I would say what's really amazing is as, we pass 20 or 30 people, we started saying, okay, let's build more than one system. Let's do multiple generations. As we pass like 60, 70, 80 people, all of a sudden we have a company. We have an R&D set of projects. We have a next generation set of projects. We have the current generation. We have a productized version that we're, getting ready to ship. I think it's really just been amazing how we've kind of all of a sudden transformed from just a bunch of, plunky PhDs in a converted office building now to a real company that has this entire pipeline. So, yeah.
That's amazing. What have you been more surprised by over the past 7 years? The progress in quantum technologies, or your challenges faced as a leader building a company?
Oh, I mean, I'll give the answer that I'm sure every founder secretly says or eventually does say, which is so much of my job is about people. I think when you go and start a company as a very technical founder, I think you think, okay, I'm going to do this and I'm going to do that, and then all these like people issues are going to be the things that happen, 1 hour a day. But at the end of the day, like I spend the vast, vast majority of my time with people and interacting with people and solving their challenges. And yeah, there's still fundraising and there's still technical work. But by this time, I mean, it is, a very, very tiny fraction. And that most of my time is spent with people and managing people.
Is that a challenge for you as a physicist, as a technical person? Is that something you like, or would you like to take on more the role of the technician?
I mean, I think that there are aspects of it I like. I mean, like any founder, I'm sure people who think, okay, I thought I got in this for the technology and so on and so forth. But I think what's been really amazing, even in the last, like I said, year, 18 months, has been the transformation of having this kind of full-fledged company with a full-fledged pipeline. That's very, very, very exciting. And
Mhm.
something like that is only ever possible when you find the right people to join the company, when you find the right leaders, and bring them together to actually form this like multifunctional unit.
Yeah, I think it's just also just realizing that coming out of a very exotic space, which is quantum, out of a place that is bolder, and then all of a sudden, having the attention of the next big thing and the technology that has gone into, companies such as Microsoft and Google, and with NVIDIA taking up, a vast majority of their marketing and spending and just commercializing and even going out to more of a mainstream audience. I might imagine that is also very exciting to be a part of.
It is. I mean, it's certainly not what I would have expected at this stage. Like the mainstream interest, I would have always thought, yeah, there's going to be interest in quantum computing, certainly from governments, and that's only increased over the last few years. And I would imagine these giant hyperscalers as well. But I do agree, it's much more in the mainstream than I would have thought possible. In fact, I remember like a few years ago, like we got mentioned in like a Blake Crouch book. And I was kind of amazed by that. Because not only, first of all, I guess quantum computing is a very like, niche thing that is very science fiction-y, but the
Right.
fact that he went and found, a specific company or a few specific companies to name, I thought was just so crazy.
I mean, that just buckle up and enjoy the ride, I guess. I mean, things
Yeah.
more crazy. But I also want to talk to you a little bit about value creation and how that is at Atom and how you're looking at commercialization. Obviously, the big topic at the moment. We had the theoretical approaches. We had a lot of R&D project. Then we started to talk about security, QKDs, post-quantum cryptography as a very like promising path to some revenue. You just talk a little bit about how you see the commercialization of quantum, and maybe also look at how you relate that to other approaches with GPUs, CPUs, and the whole HPC that is still not at the limits. Where are the actual commercial benefits in the near future and mid future for your company and also for the industry?
Yeah, I mean, I think that we're following the same path that HPC is going to take. I think we probably, actually, not us, but like I think others probably tried to do a different path, but it's turning out the one that's most successful is following the same path that has been trodden before, which is, start off by selling systems. So HPC started like that. You talk about like old time Cray and stuff like that. It was all about these big, installations and selling these systems and getting real experts on those systems who become, both the evangelists of the technology, but also the people who were able to do amazing things with it. So I think that when we talk about commercialization right now, I think it really is about building systems and sending them to a customer site, having them stand up, and then having them kind of build an ecosystem around that. And I think that's only going to become more true over the next 3 or 4 years, that these systems are kind of hubs for people to go work on interesting problems, build companies around, have academics come and share some of those resources and things like that. So I think that's probably what we're going to have for the next few years. I think afterwards we're back to the cloud. I think as the number of customers, balloons, you can't just have hubs like that again and again. There's just going to be a fundamental challenge about how many systems we can build. And also what is the utilization of those systems if they're all in disparate little tiny clouds and stuff like that. That's not going to be useful. And so I think the entire industry is just going to go back to a more centralized cloud infrastructure where you have tons and tons of quantum computers accessible, via an Atom computing cloud, via Microsoft cloud, via an Amazon cloud, so on and so forth. Um, Afterwards, I think what's going to be most important for these quantum companies is really trying to go as vertical as possible. Like I believe that the vast majority of the value is going to be created in the solutions. and that you need to have, people on the atom computing team who are experts at essentially supplying solutions to customers and not just supplying hours of time to customers. Now, I do believe fundamentally you start out with hours of time or firstly systems and then hours of time, because I think that's where a hardware company, and I also think that, the stuff has to exist before you, invest in hundreds and hundreds of people who are just entirely focused on, this chemistry problem, this materials problem, this optimization problem, and so on and so forth. But I do believe that at the end of the day, you don't need any quantum computing expert in every company in the world. Instead, what you need is someone who goes and finds the right quantum computing company to go and solve that computational challenge for you and then integrate it into your everyday workflow.
When I listen to you, and maybe this is a misconception, it seems like you're very bullish on neutral atoms or quantum computers replacing classical computers as it compares it to more of a hybrid approach. Is that something that is right, or are you?
No, I don't think. I mean, I actually think that in the end, I didn't have this idea when I started the company because it didn't really exist, but I now believe it, which is that, what gets run on a quantum computer is not going to get chosen by a human. Maybe in the next few years, but by, 5-10 years from now, I don't believe that humans are going to be the ones that decide what gets run on a CPU, what gets run on a GPU, and what gets run on a QPU. I think instead we're going to have, lots and lots of code written by computers. And I think we're going to have AI that's helping us understand when you have an algorithm, what are the pieces that should go best on a quantum computer? What are the pieces of that algorithm that should go best on a GPU? What are the pieces of that algorithm that are best on a CPU or whatever? I believe that everything is going to work in tandem and that what we're doing is creating a tool. And I think that tool is going to be really, really useful. Don't get me wrong. I don't want to undersell it. But I think it's going to be just a tool in the toolbox of, complicated simulation and computation. And then it's about building atop that and making sure you have access to all of the, best simulation and kind of algorithms on top of that to make sure you get beyond that abstraction barrier of, something deeply mathy to something that's, solving someone's problem.
These capacities, though, I mean, this is unlike anything we have seen in human history. I mean, the Industrial Revolution was basically taking physical work. We still had a lot of knowledge work to be done. Where do you see this heading? I mean, we talk about AGI, it's very fluffy definition on how to pinpoint exactly what it means, but the scenario of that, the scalability, and also the magnitude of impact that comes from the scalable quantum computers, the challenges you can take, and you have been very outspoken on the intersection of, I would say, quantum artificial intelligence, QAI, or like the intersection of the collaboration between algorithms and AI and quantum computer. Where do you see this heading? I mean, are you worried? Are you positive? Where are the limitations? Why are you so sure that we will have these agents called human beings trying to take any decisions at all in this race of progress?
Well, I'm not worried at all. Or about quantum computing. Let's put it like that. So I mean, I believe that what we're going to do, and I think AI is going to be critical to this, is we're going to hand a set of tools to people that are just unused to having a computational tool like we're talking about. And so the example I actually fall back on are mechanical engineers and architects and things like that, which is that for my entire life, I believe mechanical engineers and architects find it or have had access to computers in a way where they go and try out hundreds or thousands, or maybe if it's an optimizer, tens of thousands or hundreds of thousands of different models before they go and build a building, before they go and build their product. And this is just a tool that they have now, which is, I think they don't even realize how special and amazing that is. And that if we went back 60 years, 80 years, those same people, their lives would and their professional careers and how they do their work would be so unrecognizable to them right now. It's like they were a different profession. I think that quantum computing is going to do the same thing for materials engineers, for chemical engineers, for chemists, for maybe even biologists one day. I believe that those folks think of their careers right now as static, and they look forward 50 years and think, well, people will be using, different instruments, but they'll still be going into the lab and doing this and that and the other thing, the same kind of way I work right now. But I actually don't believe that. I think that they will become so fundamentally different by having a computational tool where they sit down at a computer and they maybe via AI ask a question, and a simulation gets kicked off and run on a quantum computer with GPUs as well, and CPUs and so on and so forth. And it's just going to become this amazing tool where they can actually try out significantly more things than they ever could have imagined if they had to go into the lab and spend days, hours even, and to just get the result of one, run. And I think this is going to be a seismic shift for those professions.
I would agree in a positive scenario, but I'm also thinking, why do we need the prompt engineer as a human? And are we even capable at asking these questions? So in my recent book I published, we write about the externalization of building an AGI, putting the authorities into algorithms as in comparison to taking our human, whatever you want to call the essence of being a mensch, upgrading that to cope with that complexity. So the agency of asking those questions, to come up with those trigger points for AI and the computation to come up with new materials, to actually create something really new. There are two questions here. One, are we even capable of these questions once the complexity becomes at that level? And two, why do we even need that agent if the AI is capable of asking these questions itself, without even having a sentience or a self-conscious entity, but just the agency of playing with those prompts and those questions? So how do you think about that?
Yeah, I mean that's almost a question that goes beyond quantum computing. Because at least the way I look at quantum computing, it's
So
just
you're
another tool in the toolbox.
you're
But
in,
I'll answer it.
in the midst of putting the capacities. So either
Yeah.
you think of progress as a commercial aspect or as a scientist, but not on a societal level. And I think we have to think holistically about what kind of future do we want to have. And at least if it's a future that ends up like in that scenario, how do we cope with it once it hits us? I think that's a very important question to be asked also, right?
Yeah. I mean, I'll admit, I think that depending on the day you ask me, I'm sometimes a little skeptical that AGI is right around the corner. And then sometimes I'm kind of amazed at what gets done. Because I think that generally speaking, I've slowly come to this idea that, for some definition of AGI, maybe the bar is actually much lower than I realize it to be, because I think so much of what I think of as, replacing X, Y, or Z that could be done by a human turns out to be, I would say, I guess, following the heuristic rules of logic, and or language, and that it turns out that maybe that's not around the corner. Or sorry, maybe that's not too far out. Maybe that is around the corner, and we constantly see hints of that. I would say, even day to day and working at atom computing, I think as people start using more and more, complicated AI tools, we do start to see hints where it does feel like, okay, actually, if you have this swarm of agents, maybe they can do this thing that, a human, a great experimentalist can sit there and do, but maybe this swarm of agents can do it just as well. So I think that in that sense, I believe that, we're going to hit some version of AGI. Now, do we hit this like kind of super intelligence that's able to push beyond anything a human could imagine? That I worry, not worry, but I question whether we're right around the corner from that. And I think that maybe there is actually a lot to be done to go from where we are to something that gets there. And that there's a part of me that wonders, it might not just be a 10% or 20% or 30% increase in some metric, many, many, many times over year after year. You might actually need something that is a step change. And maybe we haven't seen that step change yet. So with that in mind, going back to your original question,
Yeah, sure.
I don't necessarily know if I believe we're at a point where uh that we should be nervous about handing over these tools to agents yet. Now I could see it the other way, which is okay, well, if then a step change happens, and things always happen faster than you think they're going to, especially in the AI era. So maybe a step change happens, and all of a sudden, 6 months after that step change, we really do have some kind of actual intelligence that is beyond a simple definition of AGI and really kind of crosses that line. I mean, I do see the idea that complexity goes faster than humans can understand it. I generally believe that. So yeah, I think that a human could get cut out of the loop, and that would be kind of very science fiction-y, but it does seem quite possible. And I think then it becomes this larger question about like, how did we even control such a thing, or is there such a thing as controlling such a thing? And yeah, that is a bit of a scary topic, even without quantum computing in the loop. Which is just to say, look, if you had access to all the compute resources in the world, and there really was something that was beyond the intelligence of a human and could operate 24 hours a day, 7 days a week, and could operate faster than a human, that is a bit crazy.
But this is what I ponder. It's like if we think there's a potential, even if it's a near future or midterm future, to have something called superintelligence or AGI, however we define it,
Yeah.
there are reasons to believe that the speed of change after that towards a technological singularity will be much shorter than the predictions of a singularity, because the magnitude of scale will then just propel into some kind of collective data processing of progress. And so with that in mind, I always think that it's kind of sort of like the same essence around the security aspect. So we do have some securities in place today, but if we believe in some scalable quantum computer, Shor's algorithms or whatever, there are very much strong reasons to believe that we will have a problem once we have a scalable quantum computer. Therefore, we think about the implications once it hits us. And I think this is where I'm going with the argument, is to say that when we play with words such as AGI or SI or a technological singularity, I think, we are in a seat where, not only because it's important from a standpoint of extending organized human life, but also in the sense of a commercial aspect, to say, can I anticipate future scenarios of progress, and how would my business model and how would the societal structures then, be? Because, based on what I see today, we strive for progress, which is a good thing. It gives us some kind of purpose. We put purpose to life. We have, great tools, as you said. We were gifted two opposable thumbs to improve the state of humanity, which is a great path. But then again, how does progress look then in such a scenario, and how can we think about and anticipate what that even means? Because right now it is the driver of our progress, is the capitalistic model, and seeing the economy, and this is also the essence of the quantum economy, as an operating system. So it's not only about the ethical foundational responsibilities we have, but can we anticipate business models? So I guess my question is here, with these capacities, what do you see as like the first industrial use cases or business use cases where you, beyond compute, have spin outs or use cases from companies that you think are really useful for humanity, that are a near-term future, where you see huge markets evolving, or completely new business cases that we can capitalize on?
Well, I mean, I definitely think it starts with materials, and the next is chemistry. Like when we talk about with the U.S. government, when we talk about folks otherwise, it's the first thing we talk about that gets run on a quantum computer are materials problems. And I think that there's lots to be done on a government level for understanding materials in a way that's just not possible with these strongly correlated electron problems or anything like that. I think when we talk about the next step up, it's all about quantum chemistry. It's all about catalytic chemistry. It's all about trying to figure out how do you, make the processes that sort of run, food production or other pieces like that, that end up taking huge amounts of energy for the world that are just kind of way in the background of actually what, it takes to have a planet of 8 billion people or whatever it is, and make those more efficient. And I think that's why it's going to be critical that quantum computing companies really make sure that they're selling the solution and not just selling time. Because I think it's going to be so important to go and solve these problems, have the experts that do that, and then work with the companies that need those solutions, and make sure that they are capitalizing on these solutions and that we are honestly getting a piece of that. So I think those are the kind of near-term projects. I think, at the same time, if you're at that scale, you're also talking about Shor's algorithm and things like that, and breaking elliptic key cryptography and so on. I mean, there's certainly one customer in America. There's probably one customer in every country that probably is interested in that. And I think that that's going to be something that as a world, we're going to have to reckon with, which isn't to say, there's post-quantum cryptography, there's quantum key distribution and things like that. So it's not going to be a question of, okay, what about the communications right now? It's going to be a question about like, well, hold on, there's, I assume, tens of years, 30 years of stored communications because someone had the bright idea, maybe we should keep this around just in case. And all of a sudden you'll have to realize, okay, that 30 years of stored information is going to be readable in the next 6 months, in the next year. And that is going to be a complicated affair, let's say, for national interests or international interests and stuff like that.
Yeah, I mean, we see that today already. And how do you see the role of governments here in this race? You work with some of the countries. You've also been titling to some of the initiatives in Denmark. What do you see on the governmental side here? Do you see governments getting, in and with equity and involved and regulating? Do you see them as a facilitator for corporates? Are we moving into like a battle of countries and regions as in, more than we have on a capitalistic side when it comes to companies?
Well, I think being part of quantum computing, I will say, there's multilateral export control restrictions around quantum computing. I think the tent is fairly large for folks who have joined that multilateral control. It's not infinite by any stretch of the imagination. And I'm sure that as time goes on and more gets done, that tent for the United States will get a little smaller and a little smaller and a little smaller. So I think that there is going to be a lot of regulation. I don't necessarily know how quickly that will come, but I imagine every time there's a new generations of systems, they can do more and more. Everything gets a little tighter. And that's true of GPUs. I mean, the current administration aside, generally speaking, I think that throughout the course of America, the government has always tried to, especially with national interests in mind, kind of limit where chips are going, where computational resources are going. And I don't expect that to be different in future administrations or things like that. So I think there will be a lot of government control over how you access these resources, and certainly where these resources can be planted. I think the question of, AI, going back to this, I think that's a huge and open question, which is, if you can get through super intelligence, if you can get to things like that, I can imagine that the government really tries to limit how that gets used and who gets to use that and so on and so forth. And I'm sure this is going to be a topic for the next dominant topic, hopefully, not hopefully, but interestingly, over the next 20, 25 years, is that the rate of change of what can be computed, of what uh, what computation allows one to do is just so fundamentally different now and in the future that governments are going to have to figure out what it means uh, to control these resources.
Yeah, I like your way of thinking, Ben, and you just reflect on topics that throw out some questions that are a little bit outside of the technical aspects that you probably talk about, and therefore I just like to play with that. We could always talk a lot about your new company and endeavors, but I think also one of the reasons that I want to have you on is you seem to be a person that take on a question and think about it, and then comes back with a profound answer on that is one honest and also reflected. So I don't want to let you totally off the hook when it comes to that
Yes.
future scenario. If you don't mind, if I would say that Gen AI is more data driven. It's trained on simulation of data that is given. Would you agree that quantum is more reality driven?
Oh, absolutely. I would call it, it's, if you call Gen AI or just AI data driven, I would actually refer to quantum computing as computation driven. And so I think of quantum computing as very small data in, complicated algorithm being used, very small data out. So I think it's a fundamentally different way of doing computation compared to AI. And I also think that's going to change how business models work as well. So when we talk about cloud computing right now, really cloud computing, I would argue, is really simple algorithms where you stuff data in on one side, you send it over the internet to your cloud system, and it stuffs data out on the other side, probably to person or on your phone or whatever. And I just fundamentally think there's a difference there between what classical computing is like and what quantum computing is like. Because when we think about what quantum computing is going to be like, it's going to be, I ask a question that's buried in some algorithm, and there's very, very little data that flows into and out of that question. There's going to be a right answer, hopefully, to that question, and you have to go and have the quantum computer actually go and calculate it, but you're not shoving tons and tons of data into it. Now, the other flip side to this, I would argue, is can you kind of combine these? Which is to say, can you feed an AI data that comes from a quantum computer? And I think the answer is probably yes. I think there's been papers, as far back as 2017 that were starting to look at this, which were to say, maybe an AI can't be a perfect quantum computer, but maybe it can generally understand the things that come out of a quantum computer. And how do you do that? You have to have training sets. And the only way to get those training sets is to have a quantum computer. So I do believe that there's going to be, some complicated interface where, you have quantum computers whose sole job it is to calculate things for AI, like for something to actually have some kind of quantum data pool. Which when I say quantum data pool, I don't actually, there's different kinds of AI and different kinds of quantum data. I mean classical bit strings output from a quantum computer. So it's much less boring than I make it out to be. But you have a quantum data pool of calculations that come from a quantum computer. And I believe that there will be interest in building AIs around that data and around training on that data.
I like that. I like that difference that you made, but I also think that quantum is also once now humanoid robots. And we just had a recent launch on the first commercial product. Start to learn and train and interact on physical reality. The quantum computational part that you just talked about. That's what I meant by reality driven. So when we look at exploring progress. So progress today, if we look at information as packed knowledge and just having a knowledge society where we as a species have not been good enough to sort out all the variations within a given data set, that to me is basically where we are on AI. We are trying to figure out creativity within a given data set, right? And what I think happens when we start to play with reality or what we perceive as reality, we take humanoid robots that are interacting with reality and we start to expand our periodic system with new elements. We kind of sort of tap into, I would say, the physical perceived reality, the boundaries of physics as we see them. but not in a given data set. So what I mean, quantum could be reality driven. The fusion of the two, of AI and quantum, moves beyond knowledge, right? Because knowledge, the information processing of sorting it out, is not understanding. It's not the human endeavor of creating actually something new. And I think, right, that this is where I think, and this is not, solely based on quantum compute, but it's basically, it will be enabled through quantum computing if we have chips that are, localized and are driven on these entities that could play with reality. Where do you see, coming back to my previous question on human creativity, what do you see, like, what kind of changes to how we live and how we perceive reality could you, you said science fiction, but I think it's more science philosophical, but a PhR sci-fi. Are there any visions that you can think of, that things that might really shake up how we perceive reality once we have more compute or more data structures?
I mean, I think what we'll end up in my wildest hopes, what we will end up having is, a transformation where, there's another manufacturing revolution. And it's just that manufacturing revolution or industrial revolution happens on a wildly, wildly different scale. Like, I think that if we can have compute resources which are allowing us to really understand materials and chemical interactions, beyond what you can do with mean field, beyond what you can do with DFT, I think the idea would be, can we actually create materials that have properties that utilize quantum mechanics in a fundamentally different way to create some people call them designer materials, but materials with properties we're just not used to. And I think that if we can do that, and I think quantum computers are going to be a key aspect of that, I think that what we build afterwards is going to be quite amazing. And I think, the thing that people always come back to, over the past, tens of years is superconducting systems. I mean, could we imagine a world in which, not at high pressure, but at room temperature, you have superconductors, and there are superconductors that are just a part of everyday life. And I think that's the difference. It's not just the question of, oh, can we have maglev trains and all these amazing things that, operate at very, very low cost in terms of power and so on and so forth. But the real question is, what's it going to be like to live in a world where that is so mundane that kids play with toys that use superconductors, because it's so cheap and so easy to build, because we have figured out what you need to do, that it's just a part of everyday life. And I think that goes beyond that, because I think that just generally, you can go and say, look, there's all these problems, degradation of batteries and things like that. Well, maybe there's a way we can figure out a new material that's using some property of quantum mechanics which resists that. What if batteries could last for not hundreds or thousands of cycles, but hundreds of thousands of cycles or millions of cycles? And I think generally speaking, I would say this is the world where I think we would have a fundamentally new, like I said, materials revolution, industrial revolution, where all of a sudden, instead of just having, computer controlled manufacturing equipment, you have this new idea that materials, like custom designed materials, are the norm. I think that would be kind of amazing.
No, I totally agree with that. And if you look at that on a practical level, if we have that scalability or we had a capacity, then we don't have an energy problem. We have a storage and distribution problem today anyhow, right? So the marginal cost of energy would plunge towards zero. A world with abundance of energy would look very much different than the one that we have today. And yeah, so, but I mean, is it then, do we need to, it seems like we then have to stabilize truth and knowledge. We have to baseline world models. We cannot rely on the probabilistic logic of quantum systems, because, if that is given, then, you could argue, is truth a probabilistic outcome of a distribution system in quantum? Is that how we'll see it? Or do we need to take, very foundational decision on what knowledge and truth even means?
I think this goes back to, the basis of quantum mechanics in general. And I mean, I've definitely, reflected on that as being been a physicist for a while now is I'm definitely in the, what is it called? The, shut up and calculate camp. So I haven't given, deep thought processes to what does it really mean to do measurement and have a wave function collapse. But at the same time, I will say, I've gotten very, very comfortable with this idea that, you go and you very carefully understand, all the implications for what a measurement or something akin to a measurement really is. And I've just gotten comfortable with this idea that you can always put a lot into that measurement and kind of have everything work out the way you want it to work out and have your reality seem pretty reasonable. Because so much of reality is that measurement effect, whether that measurement is human driven by putting a camera somewhere, or measurement is just the nature just seeing a photon. I think I'm okay with the probabilistic nature of quantum, I guess, in that sense.
Yeah, I'm sorry for getting you
Sure.
philosophical realm. I just like how you pick up the answers and play with them, and or the questions and play with them. And how far can we take it? Do you see like parts of the body? Do you see consciousness, the brain having quantum physical phenomena? There are theories on microtubuli and how the brain operates. Could you even imagine the brain being a wet and fluffy quantum computer built in a very much different way than using neutral atoms or superconducting? But
I don't know if I believe that. I do think I think that quantum mechanics. So I'm trying to remember if this is accurate or not. So I'll give the big caveat that this might have been disproven a long time ago, and I'm just behind on this. But my understanding was, at some point, folks had been looking at, how birds could potentially be using magnetic fields to do actual navigation. And they came up with a pretty quantum mechanical explanation for it, which I think was some variation of the Aronoff bomb effect, which was that they were kind of sensing magnetic fields in their eyes using quantum mechanics. And so I do believe that, quantum mechanics is just a normal part of everyday life in that sense. Usually it's masked by high temperatures and things like that. But I believe that it is a tool. And if biology has enough time, it uses that tool and builds around that tool. Now, I don't know if that really means that consciousness is based off of quantum mechanics, but I do believe that means, it's not as exotic as people think it is. It just happens to be a very counterintuitive way that nature works. But that is how it works. So that's how that's how biology builds around it. And so who knows?
So again, thank you for that, for taking on these journeys of pondering. And I want to get back to our the company structures, and I really enjoyed the conversation with you, Ben. So again, thank you so much for doing this, and give me some insights, some non-public, accessible hidden secrets about where Atom is heading. Your outlooks for 2026. What are our next milestones?
Yeah, I mean, for us, it's all about increasing the complexity of the quantum error correction we're doing. With Microsoft and with other partners, we've really shown that you can build really, really complex systems with neutral atoms. You can control hundreds of atoms. We'll show you can control thousands at the same scale. I would even say better than we can do hundreds. And it's starting to say, look, let's increase the complexity of the quantum error correction. Let's get better performance. And let's keep building the physical systems better and better. There's no wall we've hit by any stretch of the imagination. Over a year ago, we had announced at Quantum World Congress, we're still on a path where we're going to 10x the system size every time. So while we're building these 1,000-qubit systems and shipping them, we are building our 10,000 qubit system. And fundamentally after that, we want to build 100,000 qubit system and so on and so forth. And so we are pushing on both the physical side as well as what you can do on that algorithm side, as well as with logical qubits. And we see that's the path forward. It's about this holistic use of a quantum computer, and not just getting stuck on one aspect of logical qubits or one aspect of physical qubits, but making sure you have a fully working computer that a customer can go and sit down and use. And like I said, one of the cool things that I think we're going to see over the next weeks, months, years is the kind of slow push away from actually having to think about quantum circuits and having to have all the users be experts in quantum circuits, and instead pushing them higher and higher up the stack to the point where the quantum computer is just a tool that they're using.
Is there one milestone that you're looking forward to, some threshold, some data point that you are eager to reach that you think is a pivotal point for the growth of your company?
I think there's a few, but I mean, we've shown lots of logical qubits outperforming physical qubits. I think we showed repeated error correction at the beginning of the summer. I think there's more and more and more to come. Again, more repeated quantum error correction, higher performant repeated quantum error correction. I think making sure that we keep increasing the gap between the performance of logical qubits and the performance of physical qubits. I think it's hard. First of all, I think the magic of quantum error correction is what's going to save us, but it's hard because our physical qubits keep getting better and better as we go. But again, the nice thing about that is that as long as holistically the entire, physical error rate across many, many different processes keeps going down, the logical error rate will keep going down too. And so I think we're on a good track there. And I think then again, it's about building bigger and bigger systems. And I think doing it at a low, marginal cost. I think that's the, great thing about neutral atoms is at the end of the day, we start off with millions or tens of millions or hundreds of millions of neutral atoms. And the system we're building on top of that, whether it's 1,000 qubit system, whether it's a 10,000 qubit system, 100,000 qubit system, kind of looks exactly the same. Like the complications of the actual spots of light you're putting into the back of the microscope objective change, but the actual system itself, the cost of it, the complexity stays about the same. And in fact, as we get more and more engineers, more and more folks at Atom working on this, I would actually argue the systems get smaller. Turns out physicists sometimes make things big because that's the easiest way to build them. But if you hire a bunch of engineers, they're also excited about making things small. And I think that's also a huge benefit to us. So
that's a very possibilistic and not a naive, optimistic view on the future, Ben. Thank you for sharing some insights from Adam and also taking on a philosophical journey around the quantum economy and quantum physics. It's been a real pleasure. And next time, I want to sit down with you in Boulder, Colorado, the capital of the U.S. in quantum still, as claimed by Ben Bloom. And again, thank you so much, sir, for coming on.
all right. Thank you so much. It was nice meeting you.